Let's start with our xy plane, also known as the Cartesian plane. Imagine we place a point at 3, 4. To reach this point from the origin, we draw a vector along the x-axis to x equals to 3, and from there, we draw a second vector traveling straight up by y is equal to 4. The sum of these two vectors gives us a direct path from the origin to our point. Notice that these vectors form a right-angled triangle. So how do we find the length of our vector r? We can use the Pythagorean theorem, which helps us find the length of the hypotenuse. By plugging in our numbers and working through the math, we find that the length of r is exactly 5. Let's define the angle of our vector as theta. So how do we calculate theta? We can use basic trigonometry by setting up an equation with the arc tangent and plugging in our coordinates. We finally find that theta is 53.1 degrees. So, our red point can be defined by its x and y values, known as Cartesian coordinates. We can also represent it using r, which is the distance from the origin, and theta, which is its angle from the positive x-axis. This representation is called polar coordinates. Let's clear away the Cartesian plane. In its place, we'll introduce our polar plane, which is made up of concentric circles. This blue circle represents r is equal to 3, meaning that any point located on this circle is 3 units away from the origin. This orange circle represents r is equal to 5, and that's why our red point sits on it. As we rotate our point around the circle where r equals 5, notice how theta continuously changes. Alternatively, when we change the r value, it adjusts the point's distance from the origin. When we measure counterclockwise, the angle of our red point is 30 degrees. But we can also rotate clockwise. An angle of negative 330 degrees leads us to the same spot. We can also use this negative angle to write our polar coordinates. But we will stick with the simpler positive angles for this video. Earlier, we converted Cartesian coordinates into polar coordinates. But what if we are given the polar coordinates and need to find x and y instead? We can do this using basic trigonometry. First, we set up an equation to get the value of x. And then we repeat the process to compute y. These two formulas are universally applicable when converting from polar to Cartesian coordinates. Let's run through one more example with a different point. Just like before, we apply the exact same formula to calculate our x value. And the same formula to find our y value. Like I mentioned, these two equations will work for any point on the plane universally. But what if we had to convert from Cartesian to polar coordinates in the second quadrant? To find r, we apply the Pythagorean theorem. It doesn't matter which quadrant the point is in. This formula is universal, and you can always rely on it. To find the angle, we will use the inverse tangent formula from earlier in the video. But the result that we get is clearly the wrong angle. This happens because the formula doesn't account for the signs of x and y. Since our point is in the second quadrant, we must add 180 degrees to the formula's output to get the correct angle. Remember that using this formula requires caution because the rules change for each of the 4 quadrants. Instead of relying on a dangerous formula, let's look at a more intuitive way to solve for theta. We'll start by defining the acute angle alpha within our triangle. We ignore the negative signs and use the inverse tangent with positive side lengths. We know that the pink angle is 180 degrees, and hence the purple angle must be 180 minus alpha. I recommend sketching the triangle and using this kind of geometric reasoning to determine theta. We now understand polar coordinates. If you found the video helpful, you can support my channel by liking, commenting, subscribing, and hitting the bell notification icon so you don't miss future content. Comment what topics you would like me to cover next, and I'll keep that in mind.